This is the last video about improper integrals, and we're just going to do a quick little recall here about the types of improper integrals. Previously, in two previous videos, we looked at type 1 integrals. Type 1 integrals are unbounded left or right, and they are easier to recognize as improper because of the bounds that you see. You see the infinity in the bounds, letting you know right away that those integrals are improper. Type 2 is what we're going to concentrate on today, with one sort of mixed example at the end. Type 2 integrals are unbounded above or below, and they are more difficult to recognize. They are more difficult to recognize just by the integral, because the integral of an improper type 2 looks normal. You cannot see the improperness in the bounds. What you have to know, you have to recognize, is that the function f of x has some kind of discontinuity at one end or the other, or maybe even somewhere in between. So let us go and look at the definition of the improper integral, and you'll see that it is defined in a very similar way, to what we did for type 1. And so let's look here. The first part: if f is continuous on closed A to open B and is discontinuous at B. So I'm thinking about this kind of example right here that we just drew, right? Then the integral from A to B, which looks normal, is actually improper, and it is calculated, is defined as the limit as t goes to B from the left. From the left, because if this region, and I've drawn here, has a discontinuity at B, and we're going from A to B, we are approaching B from the left of the integral from A to t of f of x dx. So just like in the type 1 case, this is telling us to do a two-step process. It's telling us first to do anti-differentiation and the fundamental theorem of calculus, and second, once we have got that antiderivative, to then take the limit, right? So it's calculated in exactly the same kind of two-step process as a type 1 improper integral. So let's look here at the second part. If f of x is continuous now on open A to closed B, so I am thinking about this kind of example up here, and is discontinuous at A, then the integral from A to B of f of x dx, which again looks normal, is defined as the limit as t goes to A from the right this time, because if we are going through this region and we want to approach the discontinuity, we are approaching it from the right, of the integral from t to b of f of x dx, and it is calculated in that same two-step process. Now both of these, of course, are defined if the limit exists. And so if the limit exists, these integrals are called convergent, just like they were for type 1. And if the limit does not exist, those integrals are called divergent. And just like in type 1, there is a third possibility for type 2 integrals, and that third possibility is the discontinuity C is somewhere in between. The bounds A to B. And if that is the case, and if both side pieces are convergent, just like type 1, this only works if both pieces are, I was going to say both peaches, that's not right at all. Both pieces are convergent. The integral from A to B of f of x dx, you split it up. You split it up as one side of the discontinuity plus the other side of the discontinuity, as long as both pieces are convergent. So let's go ahead and look at a couple of examples here, and one at the end, which is going to be a bit of a mix. So the first example. Let's look at here, number 1, the integral from -1 to 0 of 1 over x squared dx. So from our knowledge of the graph of 1 over x squared, right, from -1 to 0, 0 is a vertical asymptote. A 0 is a vertical asymptote of this function, so this is a type 2 improper integral. So we're going to evaluate this by taking the limit. The limit as t goes to 0 from the left of the integral from -1 to t. So we've taken the discontinuity and we've made it t of 1 over x squared dx. ftc, so we have an antiderivative here, -1 over x, evaluated at those bounds. So step 1, antiderivative ftc gives me this. Plug in the top minus the bottom. So then I take the limit as t goes to 0 from the left of this. And of course we have this -1 over 0 negative, right, which is nonsensical, but gives us the idea that this is exploding. It is going to infinity, and that limit, therefore, does not exist. And if the limit does not exist, the integral is called divergent. So there's an example, first one, of a divergent type 2. Let's look at the second example. So second example here, we now have the integral from 0 to 1 of the ln of x dx. Again, looks normal, looks innocuous, until you remember that the origin 0 is again a vertical asymptote for the logarithm function, and that makes this an integral, an improper integral of type 2, this time with the bound on the left-hand side. So this integral is calculated as the limit as t goes to 0 from the right this time. So as t goes to 0 from the right of the integral from t to 1 of the logarithm. And this antiderivative here, this antiderivative is calculated by integration by parts. We did that previously, but so what we are using is this fact, that an antiderivative, the antiderivative of the logarithm is x ln x minus x plus c. We are using that fact here, and that is calculated by integration by parts. If you want to go and check that, integration by parts. So here's our antiderivative that we are using in the FTC. So we're doing the top minus the bottom value. So we have 1 ln 1 minus 1. That's the top value. Ln 1 is 0, so that just goes away quite nicely. Minus, and then plug in the top value, t ln t minus minus gives me plus t. We have to take the limit of this as t goes to 0, so I'm going to be a little bit careful here because I have a form here which is going to give me a little bit of extra work to do. So I'm going to split up using limit laws. So the limit as t goes to 0 of minus 1. The limit as t goes to 0 from the right of t ln t, and the limit as t goes to 0 of t. So those on the outside, right, the first and the last, are easy to evaluate. It is this middle one, which is going to give me a little bit of problem, because this is an indeterminate form. This is form 0 times infinity. And you will remember 0 times infinity, an indeterminate form, means that you need to do some more work, algebra, L'Hopital's rule, to evaluate that. And so 0 times infinity, what we are going to do is transform it. We are going to transform it by pushing one of the functions into the denominator, typically not the logarithm, anything else. So we'll push the algebraic function into the denominator, and now I have form infinity over infinity, which is a L'Hopital form. So these improper integrals, they do use limits, and so all of your limit calculation techniques from Cal 1 are brought to the forefront here. So L'Hopital's rule is a good one to review if you need to look back, and especially these forms which are not the basic ones, sort of the more advanced indeterminate forms require a transformation before using L'Hopital's rule. So now is a good time to go back maybe and review some of your procedures for that. L'Hopital's rule tells me I take the derivative on top and the derivative on the bottom. And if I simplify those two, I simply get minus t, which is quite lovely because then the limit as t goes to 0 of minus t is just 0. This minus 1 is just followed through the whole way. And finally, I get my answer as minus 1. So the integral, because this limit exists, the integral is convergent. And let's just remind ourselves what this is telling us. This is telling us that this area, the region here, as we build up area, right, going down and down and down and down forever, that area is tending towards minus 1. Minus 1 because it is below the axis. It is negative. That's example 2. Let us go and look at example 3. So example 3 I have done wrong on purpose to start to show you. So let us do here the integral from 0 to 3 of 1 over x minus 1 dx. And you will notice that there is no problem with the 0 and there is no problem with the 3. Right? So you might, this is sort of extra hidden problems with this integrand, because the bounds like in the previous two examples are not discontinuities. The discontinuity this time is hidden in the middle, right? The discontinuity is at x equals 1, and if you weren't paying attention, you might launch yourself into a calculation like this. You might say, well, this integral can be calculated using the FTC, which it cannot because it is discontinuous, but you might not notice. And you might say, well, this is the antiderivative that I'm looking for, the logarithm, the ln of the absolute value of x minus 1. From 0 to 3, you might plug in those values, top minus bottom, and you might say, well, then this gives me an answer of ln 2, and you would be wrong. You would be wrong because you have used the fundamental theorem, which applies to continuous functions, and our function is discontinuous in this interval. So what do we do? What is the right way of doing this instead? So here is our function. X is equal to 1 is a discontinuity, So the correct way of doing it is what part C of our definition up there told us, to split this integral up at the discontinuity. To split it up at the discontinuity. And then we have two improper integrals of type 2. And the original integral will converge if and only if these two pieces converge separately. So I go ahead and do the calculation for each of these separately. So I have the limit as t goes to 1 from the left, 0 to t of the same function, and then the limit as u goes to 1 from the right of u to 3 of the same function. So we're going to go ahead and calculate the antiderivative. The antiderivative above was indeed correct. The ln of the absolute value of x minus 1, this time from 0 to t here, and this guy, the same antiderivative from u to 3. I'll focus on this guy for the moment. So the limit as t goes to 1 from the left, plug in the top minus the bottom. Here we get the ln of 0 plus. Here we get the ln of 1, that is 0, but the ln of 0 plus, well, that is the asymptote of the logarithm, that is going to negative infinity. And because that has happened here, I don't even need to know. I don't even need to fill in these details, because if one of those two integrals, right, we split this up into two pieces. If one of them does not exist, then the whole thing does not exist. Right? They both need to converge. For the original integral to be convergent. since we have one that is divergent, it does not even matter what the other one does. It might converge, it actually doesn't, but it might converge as well. It does not matter because one piece has failed, the integral is divergent. And there's an important little point here to mention about this function geometrically. It is very tempting to say, well, what if I took balanced pieces? What if I took a piece here and I took a similar, not a similar, an exactly the same sized piece over here. And I said, well, look, by symmetry I can say that the integral, the value below and the value above are going to be the same, but this one will be negative and this one will be positive. So they should cancel. If I do the integral across that discontinuity, I should get 0. And geometrically, that seems to make sense. The only problem is you cannot do an integral across the discontinuity. So by definition of how improper integrals are defined, these do not cancel. These do not cancel. So it seems like geometrically they should, and it's not a bad geometric intuition, but by definition, these two regions, they will not cancel. They do not cancel. So let us look at one last example here, and an improper integral, which is kind of fun because it is improper of both types here. So the integral that I want to show you is the integral from 1 to infinity. So obviously it's type 1 here because we see the infinity, and it is also type 2 because the denominator would be 0. So here's the graph of our function. X is equal to 1 is a vertical asymptote, and we are considering this integral as we go to infinity. So it is an improper integral of both types. So what do we do for that? Well, we just pick some point in the middle. It doesn't matter which, and I have chosen root 2 because I know where I'm heading, and I know that will be a nice value, easy to evaluate, but it actually, I mean, it could be anything. It does not matter. I pick some value in between, and as long as both of these pieces, just like the last time, both of these pieces converge. That was so difficult. I was looking for the word there. Converge separately, then I can add them. I can add their values together, and that will be the value of the integral. So let's take a quick look. So I have split these up into the limit as t goes to 1. That actually should say to 1 from the right, because I'm approaching 1 from the right. So the limit as t goes to 1 from the right of the integral from t to root 2. And then the limit as u goes to infinity, root 2 to u of the same integrand, the same function. This function you might recognize from Calculus 1. That is the derivative of the arcsecant. That is the derivative of the arcsecant. So I have the arcsecant from t to root 2 from the first integral, the arcsecant from root 2 to u in the second integral. Now, the arcsecant tends not to be the most popular function around. I'm not particularly fond of it myself, and so I'm going to just switch it around. I'm going to switch it into a function that I am more fond of and that people do tend to know better, and that is the arctangent. So I'm going to do this. I'm going to use the age-old technique of the right triangle to rearrange these. These values are all positive, and so I don't have to worry about negative signs or anything like that, and my triangle will give me the correct answer. So if I let theta equal to the arcsecant of x, that is telling me that the secant theta is x, or x over 1, which is the hypotenuse over the adjacent. So I have placed my x on the hypotenuse, my 1 on the adjacent, and that has given me the square root of x squared minus 1 on the opposite side. So the tangent the tangent is the opposite over the adjacent, which is the square root of x squared minus 1 over 1, or just the square root of x squared minus 1. That is the tangent of theta, so theta, which was the arcsecant. So this is telling me that this is also equal to the arcsecant of x for these values, for this range anyway. The arctangent, right, if I solve for theta, I'm getting the arctangent of the square root of x squared minus 1 that I can replace here instead of the arcsecant of x in my antiderivative in case I like that function better. So I have the antiderivative now as t goes to 1 from the right of the arctangent of the square root of x squared minus 1 from t to root 2, the same function over here from root 2 to u. We'll go ahead and plug in those values, top minus bottom, and top minus bottom. Those values are pretty easy to evaluate then, so the arctan of 1 is pi over 4. If I plug in t is equal to 1 here, I'm going to get 1 squared minus 1, which is 0. The root of 0 is 0, and the arctan of 0 is, well, 0. Over here, as u is going to infinity, we are going to get the arctan of infinity. So we do need to know the arctangent graph, and this is why I chose the arctangent over the arcsecant, because most of you will know the arctangent graph, whereas you will not know the arcsecant graph. The arctangent, as we go to infinity, heads to pi over 2, so that is this value here. And then I have the arctangent of 1, which is pi over 4. Those values cancel out, and I have 0. And so the final answer is pi over 2 units. So that's kind of fun, I think. We have this region here, which is improper, unbounded in two ways, on two sides. It's unbounded on the right and it's unbounded above, and yet the area of that region, as we accumulate area in both of those infinite ways, is tending to pi over 2 units squared.